Hello, welcome to TrueRender, and this is the technical walkthrough. The project is hosted on Google Colab, and essentially a user uploads an object image, enters a text prompt that describes the image, and this text prompt is used by the SAM 3D model, which is a segmentation model, and it segments the object in the image, crops it, and uses that as an input to the TripoSR, which is a image to 3D mesh transformer, and this outputs downloadable OBJ GLB file that you can use for 3D object rendering, for AR previews. The important thing to note of this project is it's not just like an experiment or a quick project that I did. This entire repository includes a FastAPI backend, browser frontend, Colab setup notebook, the production reconstruction pipeline, some evaluation images, and some other research notebooks that I implemented that all came together for our final pipeline. Essentially, it starts in the web UI where a user will input an image and a prompt. For this case, we used this image of a mouse on a table. Describe the image, then the model outputs this 3D rendering model that you see here, and this all is being, it gets it from this endpoint right here, reconstruct, where that endpoint accepts the uploaded file and prompt, creates the ID of the job, stores the job state, saves the input image, and starts the reconstruction as a background task. Then so the actual life cycle of the job goes into the backend first, where it gets segmented in the segment and crop, and this calls generate mesh, which converts the OBJ to JOB and exposes the final mesh URL, object URL, and JOB URL. The status endpoint is in lines 120 down here, and the front end pulling logic. So this is the app code of our project, and essentially once a user uploads an image in the front end, it goes into the reconstruct image endpoint down here, and essentially the endpoint accepts the uploaded file and prompt, creates the ID of the job, stores job state, saves the input image, and starts the reconstruction as a background task. The actual job lifecycle happens in segment and crop over here, which calls generate mesh, then converts the OBJ to JOB and exposes the final mesh URL, object URL, and JOB URL. This is then shown in the front end. So this just handles the interaction between the user and the project, whereas the actual ML pipeline is in pipeline over here. So the production machine learning logic lives in this file, and essentially the loading path is shown here below in load models, and it verifies the TripoSR runtime, patches it when needed, and runs a child Python import probe, which builds the SAM 3D video predictor. This matters because Colab package state can drift, so the app verifies its runtime before servicing jobs. Then we go here in segment and crop. This is the segmentation stage. Even though the app uses a single uploaded image, it uses SAM3's image/video image interface. It saves the image as a JPG, starts a SAM session as the user's text prompt, propagates the mask, and saves both a binary mask and an RGBA image. The mask is clean with morphological open and close operations, shown here, before it becomes the alpha channel. The canonical crop logic is seen over here, right here in this code. And essentially what it does is it scores mask candidates by area, bounding box area, fill ratio, and center penalty. Then chooses the best object crop. It passes the object, square crops it, and resizes it to 768 by 768 and saves it as a PNG. That pre-processing is a key technical contribution because image to 3D models are sensitive to background contamination, off-center objects, and clipped inputs. This is why segmentation is important for this pipeline. Here, this is where mesh generation happens, and the canonical crop is composited onto neutral gray RGB background in lines right here, because Tripo expects an RGB input image. So the code then runs TripoSR as a subprocess and marching queues resolution. This is the generating mesh logic, and essentially the canonical RGBA crop is composited onto a neutral gray RGB background because TripoSR expects an RGB input image. This code then runs TripoSR as a subprocess with no removed background, and essentially this is because it's intentional that SAM3 already produces the object mask, so we don't want TripoSR to run a second background removal model and potentially create inconsistent masks. After TripoSR finishes, the app finds the OBJ output and returns it. This is down over here. This is then converting to OBJ and GLB for browser preview. On the front end side, basically it polls every 1.5 seconds. Once the job is done, it sets it as a model viewer source, and then we finally see it back over here. So it returns it back. We can see it in the front end. The final machine learning architecture uses two pre-trained models for inference and integration: SAM3 for text-guided segmentation and TripoSR for single image 3D mesh generation. Research versions that I tested beforehand used additional models and approaches, such as grounding dyno, which was used to detect the object and produce a better phrase for the SAM model right here. VGGT was used as a vision transformer for camera pose and point estimation in another one. 3DGS and 2DGS were trained as a reconstruction pipeline, and then Sugar and TSDF were used as mesh extraction attempts from splat representations. And the problem with this, even though the extraction was pretty accurate, a lot of fragments, a lot of like noise. This may have been done been because of the white background that initially I was doing, but also it took a long time to train and eventually output this mesh, up to like an hour. It was not practical to the final goal of having something that was quick and easy. We replaced the slower post-recovery with VGGT using grounding dyno to find the object phrase, train it using 2DGS, and tried a basically surface rendering extraction, and the frame pre-processing is visible here. Pre-processing where we use grounding dyno, and it was able to find the object. In this case was the hydro flask container as the prompt, passed it into SAM3, and this was our masked, basically final segmented output. Passed it into the 2DGS training. We measured a L1 score of 0.004936 and the peak signal to noise ratio of almost 31 decibels, which was still pretty good. However, when we tried to construct the mesh, it actually failed. It had up to 3 million faces and then 1.8 million vertices, and essentially it was just another fragmented image. TrueRender combines segmentation, pre-processing, image to 3D generation, evaluation, and deployment into one machine learning system. And I hope to contribute more into this in the future to get more accurate 3D models. Thank you.